In this video we will look at a situation where the auxiliary equation has two equal roots. In the last video we considered the cases of two distinct real roots and complex roots. So here is two equal roots. That happens when b squared minus 4ac is 0. So as a reminder, here's the auxiliary equation. A, b and c are the constant coefficients of the differential equation, and if b squared minus 4ac is 0, then we have minus b plus or minus 0 divided by 2a. We're only going to get one solution, because whether we take plus 0 or minus 0, we just have one solution, and the solution is given by minus b over 2a. Anyway, the solution of the differential equation that the auxiliary equation is got from is given by a plus b times x times e to the power of kx, where k is the single solution of the auxiliary equation. A and b are arbitrary constants. So notice in here that we have a product of x and e to the kx appearing. Of course, we just have a times e to the kx like we've seen before. Now we're going to show that such a product x e to the kx is indeed a solution of a differential equation whose auxiliary equation has equal roots. So we're going to take the general case of an homogeneous second order differential equation. Here's the auxiliary equation that goes with it, and we're supposing that it has equal roots. In other words, b squared minus 4ac is 0, and we're going to verify that x times e to the power of that root times x is a solution of the differential equation. So the root here is called k1, but we could just call it k. Anyway, let's verify that that's the case. So we need to plug this solution back into the differential equation. So there's y. We have to take the derivative, and we have to take the second derivative. Now, since we have a product of functions of x, we have to use the product rule to differentiate this here. So let's just run through that here. Y prime is just dy dx, of course. So we take one of the functions, let's say x, and multiply by the derivative of the other function. E to the k1x differentiated gives back e to the k1x, but then we have to multiply by the derivative of the power, which is k1. Next we take the other function, e to the k1x, and multiply by the derivative of x. Differentiate x with respect to 1 gives us, or with respect to x gives us 1, and we can factorize out e to the k1x. So we get this result here. Now let's get the second derivative. So let's take this function here, e to the k1x, and multiply by the derivative of this. Well, the derivative of 1 is 0, the derivative of k1x is k1. Now we take what's inside the bracket, 1 plus k1 times x, and multiply by the derivative of the exponential term. Well, that's going to be k1 e to the k1x. We can factorize e to the k1x out of this. Right, so we have k1 times k1x over here. Well, that's k1 squared x. And then we have k1 times 1 here. So we have a k1 e to the k1x, and we have another k1 e to the k1x. So we have 2k1 times e to the k1x. So next we substitute these three things into the differential equation. So there's the second derivative. And the e to the k1x has been factorized out. Here's the first derivative. We can take e to the k1x, and we've c times x, c times this here. So if we take e to the k1x, we're left with c times x. Now, so we can take e to the k1x out of the whole lot. And inside the chain brackets we can factorize x out of three terms. So we've ak1 squared plus bk1 plus c. But we see here that this is just the auxiliary equation with k1 substituted in for k. And we know that that's going to be 0, because k1 is a root of the auxiliary equation. So the coefficient of x is going to be 0. Also, we know that a root of the auxiliary equation looks like this. This is just the formula for solving the quadratic equation. And as we saw earlier, since we just have one root, then b squared minus 4ac is 0. So we get minus b over 2a. So k1 is actually minus b over 2a, as we saw before, and we can rearrange this to multiply both sides by 2a, and we see that 2a k1 plus b is 0. So this part is 0 also, so we have 0x plus 0, so the whole thing is 0. So that proves that x e to the k1x is indeed a solution of the differential equation. Let's take this example here. We can just go directly to writing down the auxiliary equation, or we can go through the business of plugging in the trial solution e to the kx. Now if we solve this quadratic equation, we just get one root. That root is minus 4. Now we know from the previous result that a solution of this differential equation is given by x e to the k times x, where k is the unique root, or the repeated root if you like. So the unique or repeated root is minus 4. So that's from what we've just proven. However, we can proceed as we did in the previous videos, where we know that we also have a solution e to the kx, but you can see that it appears twice. You know, when we had two distinct roots, one of them was e to the k1x and the other was e to the k2x. We could follow that prescription and get a root. This is actually also a root, because if minus 4 solves the auxiliary equation, then e to the minus 4x will solve the differential equation, because that's our trial solution, e to the kx. So we have two solutions now. We have e to the minus 4x and we have x e to the minus 4x. By the way, if we write down e to the minus 4x twice, following the fact that we have two roots here, if you like, but they're repeated roots, we get two solutions that are not independent. If we divide e to the minus 4x by e to the minus 4x, we get a constant, we get 1. It's not a function of x, so these are not independent. And we know from the first video that we can't take a linear combination of these if they're not independent. They need to be independent before we can take a linear combination of them to get our general solution of the differential equation. However, e to the minus 4x and x e to the minus 4x are independent. If we divide, say, this one here by e to the minus 4x, we get x. We don't get a constant, we get 1x. So we can take a linear combination of e to the minus 4x and x e to the minus 4x. So to get a linear combination, what do? Well, we just multiply an arbitrary constant by one of the functions and another arbitrary constant b, say, by the other function. So this is our linear combination of our two independent solutions. These are independent, and of course we can factorize e to the minus 4x out of this.